Okay, welcome to this 10-minute concept video on maths and programming. Today I'm going to talk to you about numerical derivatives. Now, these are the basis of whole areas of engineering. In order to understand these, we have to have a reminder of the calculus, and I'll explain what you should have remembered from school, but here we will talk about how we can actually apply that to get numerical derivatives. And then finally, I'll finish with an example, and this is going to be a simple example that shows you how we use this in a case that hopefully you've seen before. Okay, so let's start with an engineering example. This is a fan blade, and what we're seeing here is the effect of bird strike. You can see on the right a numerical simulation. Now you imagine these types of experiments are extremely expensive to do. And so if we can model that, that saves us time and money. So the way we model those is using what are called partial differential equations. This here is actually just Newton's law. The left-hand side is just mass times acceleration. The right is your forces, but written in terms of stresses and derivatives. Don't worry too much about the complexity of this. The key thing to take away is that we need to be able to solve these derivatives here. Similarly for fluid problems, this is an example here from my own research. We're solving the Navier-Stokes equation. Again, a form of Newton's law, but written here in terms of all of these partial derivatives. And from this we can get turbulence, we can get boiling, we can get change of fluids from gas to gases, as well as a rich variety of complex fluid behaviour that is absolutely essential to designing cars, planes, anything which is moving through a substance. And again, this requires us to be able to solve these derivatives. For electromagnetics, and this is very, very important if we want to look on electric motors, electric vehicles, wind turbines and power generation, we need to solve Maxwell's equations. Again, a set of partial differential equations. The nice thing about these problems is they are requiring fluid flow and heat transfer to cool your motors, as well as the actual stresses and solid mechanics of that. So this becomes a truly kind of multidisciplinary problem here. Beyond engineering, we have the application to films. Now, this is an example from a recent Marvel film. You've essentially here got the kind of technical demonstration of what's happening. We're modelling reality, we're modelling the road breaking up. And this is done by solving differential equations. It's solved by modelling the physics and then rendering that to look like a movie. So you can see the application of these engineering skills, these differential equations, are absolutely vital across the wide range beyond just engineering to entertainment. And similarly, you can see the same thing for games. In games, when you see objects breaking apart or falling down, that's solving differential equations. Something like Minecraft, with a bit of knowledge of programming, a bit of knowledge of some of the physics in their bedroom, someone has made a game that is essentially one of the most popular games of all time. So what I'm talking about here is a strategy for you to be able to do some of these things. Okay, so how do we do this? Well, let's start with a reminder of the calculus. And before we do that, a definition of a function. So a function is just something where for a given value of x, it has some value. So the simplest example you can think of is walking over a landscape. These have hills and valleys. As you move through the landscape, that is, you change your position, which we denote as x, the height of the hill changes. So if you're at the top of a hill, you're higher up. If you're at the bottom, you're lower. And so this function is doing the same thing. For every x position, it gives you the height you are. And so what we want to do is from that height of the hill, we want to be able to find derivatives. Now, these derivatives are just how steep the hill is at a given point. But these derivatives are absolutely vital to most of the equations of motion that we deal with. So to define a derivative, well, we take the function at some point, and what we're going to do is we're basically just going to work out the gradient. For our example of the valleys and hills, we essentially, we just measure how steep it is as a given point by drawing a line to that point. And we're doing the same thing here. We essentially just draw a line to the curve at that point, and we measure the difference between the height at x plus delta x and the value at f of x. So that's just basically taking the difference between the change in the y direction for a given change in the x direction. Now notice the change in the x direction is just delta x, just some small value here. Now, of course, it's an approximation because we're taking a continuous curve and we're approximating using a straight line at that point. So to make it more accurate, we just zoom in. We're essentially measuring a gradient that is smaller and smaller, closer and closer to that curve. And in the limiting case, we get what's called a derivative. Now, this is a bit of a mathematical trick here. And if you've ever sort of felt uncomfortable with this, you're in good company, because it's essentially this weird limit where it's a point, but it's also still got a line that's appropriate, applied to it as a gradient. It doesn't quite make sense. So the way to think of this really is it's just a placeholder. It's saying if we could take that limit, this is what the derivative would mean. It's a way of measuring the gradient of that curve, how steep that curve is in the limit that you can zoom in as far as possible. So once we've got these derivatives, we can define differential equations. Now these sound quite intimidating, but really they are essentially just like any equations you've seen before. They just have derivatives in them. And you have actually seen a whole range of these before. Arguably, the equation for a straight line is a differential equation. The gradient itself is just dy by dx. The equation for speed is a differential equation if you write it as dx, some small change in distance, by dt, some small change in time. And this allows us to define the velocity, say, at a particular point in time. And then finally, Newton's law, F equals ma, that's force is equal to mass times the second derivative with respect to time of position. So then how do we solve these differential equations? Well, there's a whole load of tricks you'll learn in kind of later years of mathematics, but the simplest way is to basically just say, well, let's not take that limit. We're not mathematicians. We're not going to take this kind of limiting case. We're going to just do the engineering thing of just approximating it. So whenever we see that, we just replace the limit with, let's just take the approximation. Minus the difference in, the difference in f at x plus delta x minus the point at f of x divided by delta x, the distance between them. So we're just approximating our derivative without that limiting case. And this is basically the whole idea behind numerical derivatives. Now what we're going to do is we introduce a notation where x plus delta x is just I plus 1, and f of x is just f of I. So what we can do is we can rewrite that df dx as I plus 1 minus f of I divided by delta x, and we can solve any of those differential equations. So let's take the example of df dx is equal to some constant a. In this example, what we do is we literally just take, whenever we see a derivative, we just stick in this approximation to it. We're just approximating by a straight line, the gradient, and then we can rearrange that. So this then gives us an equation. We can multiply both sides by delta x, and we rearrange. So we're getting the value of f at I plus 1 is equal to f at I plus a times delta x. So what this has given us is an equation where we can essentially get the value at I plus 1 if we know the value at f at I, a small distance away. So what that means then is if we know the value at I plus 1, we can get the value at I plus 2. So we essentially have a technique here that would allow us from knowing one single point to calculate every other point in the domain, just by sort of stepping through. Okay, so let's take a tangible example so this makes sense. We're taking an example of a train that starts at a position 0.5 meters, and it's at time 0, and it's going to move with a constant speed of 2 meters per second. So, you imagine a situation, it's just going to go constantly and it's just going to move linearly away from its starting position. We want to solve this using 3 steps, where each of the steps is 0.05. Okay, so the trick's the same as before. We take velocity is equal to dx dt, and we would just replace that derivative by I plus 1 minus x at I divided by delta t. And then we rearrange that. So we can get the value of x at I plus 1 from the value at x at I plus the velocity times delta t. And this then means that we can basically, for a given value of I, let's say put in a value of 1, we can get a value of x2 from the value at x1. Now we're told x1 is 0.5. So what this means is we can write the equation for x2 as basically 0.5 plus the velocity, which is 2, times delta x, which is just some small step. And you can choose this to be whatever you want. You just have to basically make sure it's not too big. And so if we do that first time, we know the value at x2 is 0.6. To get a value at x3, we basically do the same thing again. We get 0.6 and we add a small increment to it. 2 times 0.05, we get 0.7. And then finally, to get a value at x4, we basically use the value at x3 and we add 2 times 0.05 to it and get the value at 0.8. Okay, so that's the technique. We can essentially do this in Excel if you'd like to. We can basically just take the value in a particular cell and just add 2 times delta t to it and get the next value. So that was still 0.6, 0.7, 0.8. And if you plot that, you can see a straight line. So as a kind of programming application, you can do that. If you want to do this in actual programming, what you can do is you can basically just rewrite it in something like MATLAB or Python, where essentially you keep getting the value at x of 2 from the previous value at x of 1, and you can plot that. Now the reason this is important to do with programming is because then you can write a loop, and that loop will allow you to do it for an arbitrary number of points. This is 300 steps, where each time we're getting the next value from the previous one. So that's the basis now of all of these kind of engineering applications, these films, these games. We can basically step through an entire grid calculating the values. In the turbine blade, you can step through the blade and work out how the stress propagates. For this, you can step through and work out how the ground cracks up. Stress can move through the tower, or in fluids, the flow can propagate through the domain. So I've talked about the motivation for doing this. I've talked a bit about the calculus. Hopefully that's a good reminder for you. Finish with some examples of using numerical derivatives to get the velocity of a train.